Hello, and welcome to the lecture where we're going to be covering part 1 of chapter 14 on the topics of dark matter, dark energy, and the fate of the universe. In part 1, and in this lecture video, we'll be talking about dark matter. There we go. All right, so let's get to it. Dark matter, dark energy, and the fate of the universe. These are questions that involve the universe as a whole, which is implied by this photo we're looking at here of many galaxies. See spiral galaxies, giant elliptical galaxies as well. And we see a couple of stars that just happen to be in the way as we look at all these galaxies. So our goal for this first section, talking about dark matter, is what do we mean by that term, dark matter? And for that matter, what do we mean by dark energy? Well, dark matter is an undetected, so we have never directly detected it, we'll come back to that idea, form of mass, so it does have mass, that does not interact with light. Okay, that's why it's called dark matter, because it does not interact with light, but whose existence we infer from its gravitational influence. Okay, so that's what dark matter is. It's matter, so it would follow the laws of universal gravity. It attracts other matter. As far as we can tell, it appears to follow the laws of gravity exactly, but it simply doesn't interact with light, unlike all known ordinary matter. Ordinary matter interacts with light, which is to say, from a physics point of view, it interacts with these things called photons, which are particles of light. Okay, and ordinary matter includes protons, neutrons, and electrons. Okay, and the building blocks of them. All right, so continuing talking about unseen influences, let's talk about dark energy briefly, although the focus of that will be in the next video. Dark energy, unlike dark matter, is an unknown form of energy that seems to be the source of a repulsive force that is actually causing an expansion that is accelerating of the universe as a whole. All right, so it's causing an acceleration of the expansion of the universe. So it's one thing to say that the universe is expanding. It could be expanding ever since the Big Bang, for example, but the universe isn't just expanding, it's speeding up. That's what we mean by accelerate. It's speeding up in its expansion. And the explanation for that must be a huge source of energy that doesn't appear to clearly come from ordinary matter or any known sources, and that's what we call dark energy. Now, dark energy is not necessarily matter at all. That's why there's no mention of mass in the bullet point for dark energy. We don't know what dark energy is. Okay, so scientists suspect that the entire universe, the hundreds of billions of galaxies that exist in the universe, each of which have hundreds of billions of stars, stars that have planets, stars surrounded by comets and asteroids and huge clouds of gas, all of that ordinary matter, which is an unimaginable amount, makes up only 5% of the universe. So the universe is mostly not ordinary matter. Now this is mind-boggling, because first of all, the universe is so vast, hundreds of billions of galaxies, as I said, and then the fact that only is 5% of the universe, that means there's 95% of the universe which is not made out of anything on the periodic table. That doesn't include stars, that doesn't include planets, that doesn't include gases. What is that? What is this unseen stuff? Well, we suspect that a huge amount of it is dark matter. Okay? And an even bigger amount, a mind-boggling 68% of the total mass energy of the universe is dark energy. All right, so 68% is dark energy. All right. Now you might be right now asking yourself, wait, why are we talking about energy and matter kind of together, right? Because we're summing up these numbers to get 100%, right? The total matter of the universe obviously needs to be 100%, okay? But is dark energy matter or not? Well, it doesn't have to be matter, because you may know that there is a mass energy equivalence given by the first postulate of special relativity that says that E equals mc squared, okay? So that's the idea that energy and matter are part and parcel of the same thing, okay? Energy can become matter, matter can become energy, all right? It is important to point out that there's also, of the ordinary matter, only about 0.5% of that ordinary matter is actually inside of stars, and most of the ordinary matter exists as a really low density diffuse gas between stars and even between galaxies. So there's a huge amount of matter that's never been condensed, that is just very low density, very cold gas stretching out over the vastness of the distance between stars and galaxies. And that's 4.5% of the total of the universe and most of the ordinary matter. Okay? So it's just amazing that there can be so many stars, but obviously there's so much more that we don't know. So what do we mean by dark matter and dark energy? Okay, so dark matter is a name given to the unseen mass whose gravity governs the observed motion of stars and gas clouds. So, I've already been talking about this. These are two similar bullet points, but framed differently, right? Because here we're pointing out that dark matter governs the motion of stars and gas clouds. We're going to elaborate on that. Dark energy is the name given to whatever, right? Notice the wording here, right? Because we really don't know, might be causing the expansion of the universe to accelerate. So now let's look in our first section for the evidence of dark matter, okay? Because this is a prolonged experiment or scientific discovery, scientific experimentation, and scientists have agreed over the past few decades that dark matter must exist. There's too much evidence to support that dark matter exists. And there's no other better explanation, no other better theory than that dark matter is out there, and we just haven't built the detectors that are capable of detecting it yet. Okay? So our goals for understanding the evidence for dark matter, so you too can be convinced that dark matter is real, is the following. What is the evidence for dark matter in galaxies? What is the evidence for dark matter in clusters of galaxies? Because there's kind of two different arguments. Does dark matter really exist? And what might it be made of, right? What's the best theory? Because again, we've never directly detected it, but what are we looking for? What do we expect to find? Okay, so the evidence for dark matter comes down to these rotation curves, okay? So these are, rotation curves, all right? These are these graphs that are collected from data, which is coming from the observation of stars orbiting the center of galaxies. All stars in elliptical galaxies, and even, in spiral galaxies, have a very well-defined orbit around the center. The spiral spins. All the stars orbit around the center of the galaxy. There's also some rotation, although much less in elliptical galaxies, but very clearly defined in spiral galaxies. And for a long time, scientists have been looking at this data, and early on, a few scientists thought it was very strange, and more recently, in recent decades, more scientists have gotten on board with looking at this data and agreeing that it's strange. There must be an explanation, because ordinary laws of gravity without dark matter cannot explain the behavior that we see. And this behavior, by the way, is shown right here in this graph of orbital velocity as a function of distance from the center of the galaxy. All right, so this would be orbital velocities of individual stars, right? And this is so you can think of a bunch of data points collected to create this average curve, all right? And then distance from the center in thousands of light years, from the center of the galaxy, okay? Each of these names here is the name of a galaxy, okay? So these are 4 different galaxies representing real data that's been collected, all right? And we have the dotted lines where we don't have data, where we've modeled it or extrapolated between data points. The solid lines represent real data. And we see that as we get close to the center of the galaxy, the stars are essentially motionless. There's very little rotation, very little orbital rotation there. And the velocities go up as we move away from the center, and then they just sort of level off. So no matter how far we get from the center of the galaxy, the velocities remain quite similar. All right. Now, this is not what we see in, say, orbital velocities for planets. If we were looking at data for orbital velocities for planets, we would see that the orbital velocities are greatest for the planets that are closest to the star, right? Say like Mercury in our own solar system. And those orbital velocities decrease as we get further away. So as we go out into the distant planets of our solar system and we look at the orbital velocities of planets like Neptune, Uranus, Saturn, and Jupiter, with the most extreme example being Neptune, the furthest from the sun, that planet is moving much slower in its orbit. Because it's just less gravitational pull. It has a very slow orbit, and thus a very long period because it has a long circumference of orbit combined with lower velocity. So essentially what it would look like is we'd have a case where we'd have a jumping up, so a big peak initially, and then it would fall off like this. Okay, so this would be the rotation curve for a solar system. So planets in a solar system like ours. And that is exactly what universal gravity, Kepler's laws tell us we should see. Okay, we should absolutely expect as we move away from the center of mass, we get slower velocities just due to balancing of forces and an understanding of gravity. So why don't we see that in galaxies? Right? That's what scientists are asking themselves. Why do we not see that decaying rotation curve? Why do we see it flat? Okay, so we measure the mass of the solar system using the orbits of planets, just like we measure the mass of planets using the orbits of moons. That's really important for understanding the mass of a planet like Jupiter. We look at all its moons, for example. Okay, we look at the orbital period. So that's the distance from the center, or that's the time, excuse me. All right, so that's the time to go all the way around. So the orbital period is the time to complete. It would be measured in seconds. And the orbital distance, which I started to say, is like the radius, all right, which would be measured in meters. You could convert to kilometers or astronomical units or light years, whatever is appropriate. But the point is that that's the base units. For circles, we can get nice relationships between orbital velocity, so meters per second. That's how fast the body is moving. So that's its instantaneous velocity. And the orbital radius, which I already mentioned. So it's called a rotation curve. A plot, the curves we've been looking at and the ones I've been talking about, a plot of orbital velocity versus orbital radius. So velocity as a function of radius. Looks like this for planets and solar systems. Not just our solar system, by the way. We've seen this type of behavior following the laws of gravity for the thousands of other solar systems that we have recently been able to survey with sophisticated techniques recently. The solar system's rotation curve declines because the sun has almost all the mass. Okay? Well, the rotation curve of the Milky Way, as with those other galaxies that we saw labeled in the figure, it stays flat. Okay? So it doesn't decay with distance from the center. That means that the mass must be, if gravity is correct, if our understanding of gravity is correct, spread out. Okay? It must be at least more spread out than in the solar system. Well, mass in the Milky Way is spread out over a larger region than its stars. Absolutely, right? So actually, you might say, well, maybe the rotation curve is completely explainable. Maybe we don't even need dark matter because galaxies aren't like solar systems. They have mass, significant amounts of mass in the spiral arms of a spiral galaxy, unlike a solar system where 99% of the mass is in the star, like our sun. So galaxies have, a lot of mass spread throughout. However, they still do have a concentration of mass at the center, whether that's the supermassive black hole that appears to be at the center of most galaxies, or that's just the very dense packing of stars that are closer to the center. There is a lot more mass at the center. As far as we can tell, just by looking at the amount of energy that comes out, that's radiated away from the center of galaxies, there's a lot more mass at the center. The mass does decrease. It doesn't decrease as quickly as with the solar systems, but it does decrease, okay? So the mass in the Milky Way is spread out over a larger region. However, that spreading out of what we see, the actual light radiating and light absorbing matter, which is ordinary matter, because all ordinary matter interacts with light. Well, that mass doesn't explain the curve, just simply put. So that means that there must be a lot of mass that's on the edge of the galaxy, which would be dark matter. So it's mass that we can't see. Okay? Why can't we see it? Well, let's see. All right? So the mass within the sun's orbit is 1 times 10 to the 11 times the mass of the sun. Okay, so it's 100 billion times the mass of the sun, which makes sense because we think on average, our galaxy kind of being an average sized galaxy, galaxies on average have about 100 billion stars. Our sun is a pretty typical size star, so it's a very reasonable estimate. Now, our galaxies have a bit more than 100 billion stars. Also, I think our sun is slightly smaller than average because we're not all the way on the edge, right? As we can see, we're about 2/3 of the way out to the edge of the spiral arms as far as our observed data can calculate. Because we can't actually, fly up and observe our particular galaxy from afar, but we look at similar galaxies, look at how they behave, and we extrapolate the behavior of our galaxy by looking at the motion of the stars that we can see inside of our galaxy, okay? So the total mass is about 10 to the 12 times the mass of the sun, or a trillion times the mass of the sun. Okay, 10 to the 12 is 1 trillion. Okay, so stars in the local solar neighborhood, so if you look at any little part of the galaxy, including our neighborhood, well, they move randomly relative to one another at typical speeds of about 70,000 kilometers per hour. Right, that's our relative speeds to each other. However, that random motion doesn't stay once we zoom out. As we look at the galaxy as a whole, that random motion is dominated instead by a spiral motion, a rotational motion, right? So the galaxy's rotation carries us around the galactic center at about 800,000 kilometers per hour, so much faster than the random motion between stars. You can kind of think of a galaxy, a spiral galaxy, as a fluid. You can think of all this random motion as like the random motion you would see in water if you were to zoom in on individual water molecules. But if you were to, to spin a spoon in a bucket of water, well, then you would see the water start turning as a whole, despite, random motion at the small scale. Okay, but here's the thing. The visible portion of a galaxy must, based on our understanding of gravity, must lie in the heart, or deep in the heart, of a large halo of dark matter, shown here as this sort of grayish blur. Okay, so the idea is that there is the luminous spiral, there is the halo of stars, so there's another type of halo, a halo of ordinary matter, and that's what it's called, of older stars that aren't part of the spiral arms. But then outside of that, on a huge scale, right? Because we consider, that this distance here is about 100,000 light years, 100,000 light years. Well, you can see here that this distance must be, at least 500 or 600,000 light years. So a huge radius, probably spherical structure of dark matter appears to surround our galaxy. Okay? Now, is this unique of the Milky Way? Absolutely not. Right? I mean, we saw those rotation curves for those kind of scientifically named galaxies, the ones with the letters and number combos. Well, the idea is that all galaxies must be surrounded by a halo of dark matter. Okay? We can measure the rotation curves of other spiral galaxies using the Doppler shift of the 21 centimeter line of atomic hydrogen. That's how that data is collected, like the curves that we saw. Okay, so we can directly look at how fast one edge of the galaxy is spinning away from us, because there would be a blue shift as it's spinning away from us, or sorry, a red shift as it's spinning away from us. So this would be the red shift for away, because that side of the galaxy, right, because it's a disk, one side must be moving away as the other side is moving towards us. The other side of the galaxy moving towards us would be the blue shift, because anything that's moving towards us for the Doppler effect on light is blue shifted. Anything moving away is red shifted. Red shifted means shifted to longer wavelengths, lower frequencies, vice versa for the blue shifts. Okay, so we have a blue shifted edge, we have a red shifted edge, and then in the center of the galaxy, we should have no shift at all. So we should have a 21 centimeter line that matches the 21 centimeter line in the laboratory at rest on Earth. The 21 centimeter line, by the way, is a what's called a hyperfine energy level splitting for very low energy atomic hydrogen. It's a rather complicated physical explanation of why this particular energy transition exists inside of hydrogen, but it does exist. It's a rare transition, but among the trillions upon trillions of hydrogen atoms out there, it's a pretty dominant signal, and it's a signal that scientists often look for understanding lots of things about galaxies, because there's just so much hydrogen gas in galaxies. Okay, so here we're using it to measure motion, the rotational motion of galaxies. Okay, and that's how we get these curves. All right, the spiral galaxies all tend to have flat rotation curves, indicating large amounts of dark matter. Again, why are we assuming it's dark matter? Because we don't see any matter, right? If there's matter out there, we would see it. Okay, we would see it glowing, right? You might be like, well, maybe it's just not hot enough to glow. Well, all matter glows, even very cold matter, like the cold gas between stars, glows in the radio frequencies, because very cold things glow at very long wavelength, low frequency, and we can see that, right? We can basically, all matter, we should see some light signature of it, and we just don't see that, so that's why it must be dark matter. So the broadening of the spectral lines in elliptical galaxies tells us how fast the stars are orbiting. These galaxies also have dark matter, okay? So it's not just spiral galaxies. Okay, spiral galaxies can be, they're the first ones discovered with this phenomenon. We can get more detailed measurements, but we can confirm that this is a universal rule, which is great for applying something to the universe as a whole, an idea. So indeed, we see it in elliptical galaxies as well. Okay, so thought question. What would you conclude about a galaxy whose rotational velocity rises steadily with distance beyond the visible part of the disk? Okay, so if we saw a rotation curve that went up, so we saw a rotation curve for velocity as a function of radius that that kind of stayed steady and then actually gradually rose up as we got further away. What might be an explanation of that? Well, is it that its mass is concentrated at the center? Is it that it rotates like the solar system? Is it that it's especially rich in dark matter? Or is it that it's just like the Milky Way, which would be, I suppose, a normal amount of dark matter? Well, it's C, especially rich. Because if there's a ton of dark matter, right, because there's, as far as we can tell, the amount of dark matter in these proposed halos around galaxies, well, it varies. So that means that some galaxies actually might have stars on the edge that are going even faster than stars in the middle because they're gravitationally attracted to all of that matter in an envelope around the galaxy. So there's more evidence, though. It's not just the rotation. That was the first thing discovered. But since then, as astronomers, scientists have come to accept dark matter is probably out there, and we just haven't detected it, they've confirmed its behavior in other ways. Okay? So we can measure the velocities of galaxies in a cluster also with the Doppler shift. So essentially what we're doing is we're applying this idea of measuring rotation, but now we're applying it to clusters of galaxies because the gravity that holds galaxies together and causes them to, rotate, well, that same gravity exists between galaxies, so groups of galaxies are actually rotating around their center of mass. So the mass we find from galaxy motions, so galaxies rotating around other galaxies, or again around the shared center of mass, is about 50 times larger than the mass in the stars. All right, so that means there's a huge amount. Essentially, as we zoom out more, we see even more evidence of dark matter. So dark matter appears to be just so prevalent and so pervasive throughout the universe and all this space between galaxies. So it really appears to be a dominant part of the intergalactic space, okay? But again, not interacting with light. So clusters of galaxies contain large amounts of X-ray emitting hot gas, okay? This hot gas is very important for understanding past collisions between galaxies because especially hot gas is left around after galaxies have collided, and it's been very helpful for scientists for decades for just understanding how galaxies interact with one another. But there's something about the hot gas which also supports the theory of dark matter. Because the temperature of the hot gas, right, temperature being particle motion, because temperature is just proportional to the average kinetic energy of particles in a gas, tells us that the cluster's mass is 85% dark matter, 13% hot gas, and 2% stars. Okay? So it tells us that this hot gas and the cluster in general has a huge amount of dark matter. How would the temperature tell us about dark matter? Well, because dark matter is going to compress the gas. As the gas gets compressed, it gets more energetic, thus hotter. Okay? So the idea is there's something pushing down on these gases, compressing them in, making them hotter than any ordinary matter can explain. There's another piece of evidence. Gravitational lensing. And this is actually a very strong piece of evidence. The bending of light rays by gravity. This can tell us a cluster's mass. Okay? So according to another theory of Einstein, we already mentioned the special theory of relativity, which is, part of it is E equals mc squared, as well as the idea that there's a finite speed for light and a few other really important ideas that come out of special relativity. But another very famous theory from Einstein is general relativity. And general relativity tells us that matter, ordinary matter, and also dark matter for that matter, it's part of the same theory, now it is, well, that matter bends space-time, and light travels along the curved paths of bent space-time. And the consequence of that is we see light bending. We were able to confirm it about 100 years ago during a solar eclipse, and now it's used as a regular technique, this idea of gravitational lensing. Scientists use it for all types of astronomical applications. They actually use it sometimes to find galaxies that otherwise would be obscured or too faint because they essentially can act like a magnification. We're able to use it to estimate the mass of things because we can actually calculate how much the light bent, and then find the mass that way. So it can be a very accurate and independent way from, say, temperature measurements to measure mass. And when we look at gravitational lensing, right, when we look at these images of galaxies, because it gets bent and we get multiple images of the same galaxy, well, we see that there must be a huge amount of matter that isn't ordinary matter, that must be dark matter, okay? So let's zoom in on this. Gravitational lensing, a cluster's gravity bends light from a single galaxy so that it reaches Earth from multiple directions. Okay, so we see sort of multiple images of the galaxy. The gravity bends light from the galaxy as it passes through its center. Okay, so this is the bending of the light. Okay. We therefore see the image of the galaxy in the directions from which the light appears to come. Right, so as we look at these different paths that light comes to Earth, we see three versions of the galaxy, which we can actually see here, right? We can see multiple versions of the same galaxy. Look at that, right? It's lensed. It's lensed because this galaxy is behind this huge cluster of elliptical galaxies. The huge amount of mass in that cluster of elliptical galaxies is bending the light of this more primordial galaxy behind it, creating these multiple images. So through a telescope, this is the result. On Earth, we see multiple images of what is really a single galaxy. Pretty interesting phenomena, okay? So all three methods of measuring cluster mass indicate similar amounts of dark matter in galaxy clusters. So not only do they all point to that there's more matter than we can see, they all agree with each other in how much more matter there is. So this is pretty compelling evidence, okay? Oh, excuse me there. So what kind of measurement does not tell us the mass of a cluster of galaxies? So think about what we've seen so far. Measuring velocities of clusters of galaxies, measuring the total mass of cluster stars, measuring the temperature of hot gas, or measuring distorted images of background galaxies. So just think of the one you haven't seen. It's measuring the total mass of clusters stars. We don't sum up the mass of the stars. There's simply too many stars to measure each star individually and then sum it up. Okay, we could try that, but it would be an impractical method for measuring the mass of a galaxy, considering there are hundreds of billions of stars in one galaxy. Maybe with computational methods and automated telescopes, we will sometime do this to get another confirmed method of measurement, but for now we're using A, C, and D, and not B. So does dark matter really exist? Because, I mean, there's all this evidence that gravity is acting strangely or that there's extra matter out there, but why can't we find it, right? And what is it? Okay. Well, there are some options for what it could be, right? Because we have to ask ourselves that, right? It's one thing to observe strange behavior and come up with a theory, but then we need to really say, okay, well, what exactly is that theory? What is dark matter? Okay. Well, option one, dark matter really exists, and we're observing the effects of its gravitational attraction. Okay, that would be one consequence of the evidence that we see. But there is actually another option. Two, something is wrong with our understanding of gravity. Maybe we have to go back to the drawing board and come up with a new, more modern theory of gravity, right? So is that it? Is it just that we have a bad theory of gravity that is causing us to mistakenly infer the existence of dark matter? Well, the thing is that gravity is so well tested, all right? And number one fits more of the data. So far, all the evidence points towards number one. Now, that's so far, right? Scientists, if they're, another decade from now, another 2 decades from now, if there's more compelling evidence that we can't detect dark matter, or that dark matter doesn't fit our understanding of particles, well, then maybe we have to go back and just look at the data again, right? And maybe reassess our theory of gravity. So, and we have to be willing to do that. And scientists in general are willing to do that. But currently, we're focused on finding dark matter because that seems to be the more likely avenue of success, right? The more likely truth. So some observations of the universe are very difficult to explain without dark matter. And again, this idea that gravity is so well tested is very true. We haven't seen any real complaints, any real contradictions with our modern theory of gravity. Our modern theory of gravity kind of being a based on the general theory of relativity with some refinement in the 100 years since then. Because we see most recently in the last 5 or 6 years, we've seen gravitational waves. Gravitational waves are behaving exactly as the theory would suggest for gravity. So it does appear that the gravitational theory is accurate. So what dark matter must be out there then? Well, at least we think so. So there's something interesting though, something we haven't touched on. is that number, that 5% number we saw for ordinary matter. Because it's one thing to look at all this inferred evidence of dark matter, see that it would have to be a lot more than the ordinary matter that we can see. So we're saying, okay, so there's this gravitational effect of unseen matter, we call it dark matter, and it appears to be a lot more than ordinary matter. But wouldn't it be great to, as I said before, independently confirm something? In this case, independently confirm that there is 5% ordinary matter in the total universe? Well, there actually might be a way to do that. And scientists have strived to do exactly that, okay? So what they've done is they measured the amount of deuterium that exists in the universe, okay? Now they've really taken a sample, because we can't go out there and measure all the deuterium in the universe. That would be even more impractical than counting the mass of every star in a galaxy. Instead, we said, okay, well, this is how much deuterium we find in our own sun. This is how much deuterium we find in the solar system, how much we measure kind of in our local area and in particular galaxies. So taking a sampling of the universe, okay? Now you might ask yourself, what the heck is deuterium? Well, deuterium is an isotope of hydrogen. Isotopes are just atoms of a particular element that have different numbers of neutrons. They're still the same element because elemental properties are determined by the number of protons, not neutrons, but you can have isotopes at different numbers of neutrons. Every element on the periodic table has isotopes, some more common than others, okay? So standard hydrogen just has a proton. It actually has no neutrons, one proton and one electron. Deuterium has a single neutron. So it has a nucleus with one neutron and one proton. Okay, that's deuterium. Deuterium, when it's combined with oxygen, creates heavy water, okay, which you may have heard of. It's very important for nuclear reactors, okay? So that's deuterium, the isotope of hydrogen. Now, it's definitely not nearly as common as just standard hydrogen, but it's out there, all right? And we find that a certain amount of it, in fact, here's the abundance, right? So the abundance of deuterium is about 10 to the negative 5, a little bit higher than 10 to the negative 5. 10 to the negative 5 will be right here. This is a power scale, so we're going up in powers of 10. So in other words, for every about 10,000 or every 50,000 normal hydrogen atoms, there's one deuterium atom, okay? So again, not a huge amount of the population of hydrogen is deuterium. But what does that tell us, right? That is that much. Well, that tells us something about how much ordinary matter makes up of the total universe. Because it turns out that you can treat a certain phase of the Big Bang a lot like the core of a star. And when you look at stars, you can find out how much deuterium is made based on the density of the star. In other words, denser stars will actually make more deuterium because they're undergoing fusion that's more efficient because there's more fusible hydrogens that are closer together. So the fusion rate is higher. That higher efficiency fusion creates more deuterium. So when we look at that, when we compare between the deuterium that's made in different density stars, we can then say, okay, well then that means that if deuterium was made and then seeded throughout the entire universe, that deuterium would have been made in the Big Bang, when the Big Bang was acting like a giant star, a star that was the progenitor of the entire universe, right? So there's some early phase of the universe when the whole universe was just a glowing mass of energy and matter, okay? So during that phase of the universe in its early stage, acting like one giant star, there was a certain amount of deuterium produced. Well, that deuterium comes up to be this exact, abundance. Well, that abundance corresponds to a particular density, a density of 5%, okay? So that tells us that ordinary matter must make up 5% of the total mass and energy of the universe. All right, so it's a really neat way of coming at that number by comparing the early Big Bang to a star, okay? So, ordinary dark matter, okay? These are options of what it might be. Let me read the headline first, okay? Or the title here. So these are the two basic options. Now we saw two options before, right? We saw options of whether we accept dark matter really exists or we go back to the drawing board for gravity. Well, we said, nope, we're going to not go back to the drawing board for gravity. We're going to accept that dark matter exists, okay? And then I mentioned this whole idea that we can also say, well, the deuterium supports dark matter, right? Or in other words, the amount of deuterium out there supports that ordinary matter is a small fraction of the total matter of the universe, okay? So another good reason to not throw out gravity and to accept dark matter. But now we have another set of options. We need to decide what dark matter is. So either it's ordinary dark matter, which means it's matter made of protons, neutrons, and electrons, but somehow too dark to detect. Okay, so there's just something about it. Maybe it's just we're just missing it somehow. Like our detection techniques are just somehow just like we're looking for the wrong thing. Maybe it's colder than we expected, or it's sort of absorbing light in a way that we're just not familiar with, right? There's something we're missing with the way that light is interacting. So it in fact is interacting with it, because light is always going to interact with protons, neutrons, and electrons, but we're missing that interaction somehow. Okay, so that's one option. The other option is that it's extraordinary. Okay, it's a type of matter made up of particles that we've never discovered. Okay, these would be called weakly interacting massive particles, massive just because they have mass, which are kind of mysterious neutrino-like. Why neutrino-like? Well, because neutrinos are already strange particles, and neutrinos actually don't interact with light very much. They don't interact with other matter very much either. They're a very strange type of particle. So maybe there are other neutrino-like particles out there, right, that don't interact with light at all. Well, the best bet is the extraordinary dark matter, just because there's not a lot of evidence to support that we're somehow missing ordinary matter out there. So we really think, and scientists think, that instead we have these weakly interacting massive particles. But shouldn't we be able to confirm that? Okay. Well, the measurements of the light element abundance indicates that ordinary matter cannot account for all the dark matter. Okay, so that's part of the reason that this is the best bet. So the deuterium method definitely supports that there's some other undiscovered particle that constitutes dark matter. So we believe in WIMPs. Okay, what's a WIMP? Well, it's just the acronym for the thing I was talking about: weakly interacting massive particle. That's what dark matter is potentially made out of. Okay, so why believe in it? Well, there's just not enough ordinary matter. Okay, WIMPs could be left over from the Big Bang, right? So definitely there would be enough energy to produce particles like that. And models involving WIMPs explain how galaxy formation works. Okay, so we got a lot of indirect evidence of WIMPs. Okay, but have we ever detected them? No. All right. Have we tried to? Absolutely. We've tried to capture dark matter. We've built detectors which are somewhat like neutrino detectors. So trying to find these very weakly interacting particles, but nothing has shown up so far. And we've tried to create WIMPs through particle colliders. So these large particle accelerators, where you accelerate particles at very high energy, crash them together, because theories of the standard model of particles suggest that we should be able to create WIMPs. They should be part of the same laws of physics, but we've never detected them there either. And it's starting to actually trouble scientists, right? Because many people thought a decade ago, by now we would have confirmed the existence of these WIMPs that constitute dark matter, but we haven't at all. Haven't got any closer. So maybe we do have to go back to the drawing board, but it's still our best theory today in 2021. So let's summarize. What have we learned? Well, what is the evidence for dark matter in galaxies? The rotation curves were the first one, and a really big one. All right, that they indicate that most of the matter lies outside their visible regions. Okay, what is the evidence for dark matter in clusters of galaxies? Well, the masses measured from galaxy motions, temperature of hot gases, and gravitational lensing all indicate that the vast majority of matter in clusters is dark. Does dark matter really exist? Well, either dark matter exists or our understanding of gravity must be revised. Okay, but I talked about which one seems more likely. And what might dark matter be made of? Well, there does not seem to be enough normal, which is called, by the way, baryonic. Baryonic matter is protons, neutrons, and electrons. Okay, to account for all the matter, all the dark matter. So most astronomers suspect that dark matter is made of non-baryonic particles that have not yet been discovered. Okay, maybe that's a cop-out to say, oh, it's made out of something we just haven't found yet, but that's our best working theory. Okay, so we're going to leave off there, and in the next video, we'll talk about gravity versus expansion, which will be our introduction to dark energy. Well, I hope this lecture on dark matter has been interesting and informative. Thank you so much for watching.